Okay, our first video here, recognizing linear, quadratic, and exponential functions. We're going to identify a function family that would appropriately model a data set or contextual scenario. All right, let's get into it. We did some warm-ups. Here's some Algebra 1 review. This was things for you to think about on your own. We will come back and define most of this stuff by the end of the video. What is a function? What is a linear function? What is a quadratic function? What is an exponential function? Pause the video here, kind of take just a minute or two to write down what you remember about these various things. And we'll come back to them and talk about it in a minute. Okay, so what we can talk about here, you can go back to this. A function usually is just an equation. It's f of x equals, I don't know, like 3x plus 4. We have all sorts of different kinds of function, things like that. We can graph them. We have some rules, and we'll get way into those later about like the vertical line rule, that kind of thing, the pencil test and that sort of thing. For every input, there's exactly one output. I don't know how much of this was covered in Algebra 1 and how much you remember since that was a long time ago. But nevertheless, we'll cover that. A linear function, lots of people remember this whole thing. Y equals mx plus b. It'll form a line of some sort, a straight line. Could be anything except not a vertical line. This is out. Can't do that. Quadratic function, most remember that it's some sort of parabola. Could be facing down, but it's facing one way or another. Usually people kind of remember the whole ax squared plus bx plus c and maybe the quadratic formula if you learned that back then. If not, we'll cover it again this year. Exponential function, usually the graphs look like that or like that. We'll get into more of that here. So we're going to see like which of these scenarios kind of go with it. Local library holds a penny drive in which people in the community are asked to donate their spare pennies to the library. When you stop by to donate some pennies, you hear someone announce that she plans to donate pennies for 1 month in the following manner. She'll donate 1 penny today, 2 pennies tomorrow, 4 pennies the next day, and will continue to double the number of pennies each day goes after. What's happening here, you're starting with 1 and then going to 2, and then she's going to double it every day. So 16, 32, and on and on and on. So this is being multiplied by 2 each time. And that kind of gives us what we need to know. And we'll come back and cover again what we think this is, but yes, this is going to probably be an exponential function. And we'll, again, get some better definitions of this in a minute. Kieran has an air-conditioned unit installed in one window of his house. Droplets of water fall at a regular interval from the air conditioner onto the patio outside the house, forming a small circular puddle. As the water continues to drip from the air conditioner, the circular puddle increases in area. Area is a big word there, big player. Kieran tries to calculate the puddle's area and observes the puddle's radius increases by 1 centimeter every minute. This is going to end up being a quadratic. We will talk about why that's that way in a minute as well. It has to do with its area. An area of a circle is pi times the radius squared. So now this is our variable, and the exponent stays the same. The exponent's constant. When the previous one, we'll find out an exponential one means it's reversed. It would be like 2 to the x instead of, like in this case, x to the x squared every time. Okay. Javon is on vacation in New York City and wants to use a ride-sharing service. One particular ride-sharing service charges a flat fee of $2.50 and an additional charge of 35 cents per mile. So this is literally going to go up by 35 cents every mile. That's a good old linear. Okay, so let's get our definitions. Oh, I'm sorry, here's one. Cheng Li tracks the temperature for a particular day in September. She notices that it was 54 degrees at 6 a.m., 60 degrees at 9 a.m., 67 at 12, 60 at 3, 54 at 6. Basically, this is none of the above. There's no real pattern to the data there or anything. Okay. There's a Desmos thing you can look at there if you would like to as well. It's a pretty interesting one. Okay, so let's start by defining a linear function. The fancy math definition is a relationship between two quantities with a constant rate of change. This will be a lot, I mean, obviously you can look at graphs and see this, but like we'll see this in a table here in a second. Characteristics. Big one is there are no exponents for any variable. If there's no exponents for any variable, then we've just got a linear. You usually just have the one variable. Constant rate of change. Well, another way to describe rate of change is the slope. If you can calculate the slope, you've got a linear thing, because a parabola doesn't have a slope. A exponential function doesn't have a slope. The graph is any non-vertical straight line, often expressed in various forms. Mx plus b or y equals mx plus b. Fx and y mean the same thing. Might have seen it like that. I'm going to add one as the AP Stats teacher. We have to be difficult, and we don't use mx plus b. We use y equals a plus bx. Don't need to know that now, but for stats, it's because you're starting on a graph at this and then increasing or decreasing by that. It kind of puts the starting point first, but stats has to be difficult like that. They like to make things different. So examples. I mean, there's some just straightforward. Notice here, if you're not even sure about this, just notice no exponent on the x. That's a linear function. We've got a graph, we've got a table. Notice this. 11 minus 16 equals 5. 6 minus 11 equals 5. 1 minus 6 equals 5. Negative 4 minus 1 equals 5. This is constant. That's a linear. If the change is constant, it's linear. Non-examples, this is a quadratic, this is an exponential. That graph is obviously something in graph that isn't a straight line, not vertical lines either. Okay, so let's talk about exponential functions. A relationship between two quantities with a constant ratio of growth or decay. Ratio means you're multiplying by the same thing every time. Instead of subtracting like we just did, we're going to divide. Constant ratio of growth or decay. Graph is asymptotic. That is kind of what this looks like. Asymptotic means like it approaches the line but never crosses it. Don't worry about the fancy math word yet. We will get way more into that later. The variable is the exponent. So it's a constant to a power, to an x power, to an unknown power. Often expressed in the forms b to the x or a times b to the x. Basically, you're looking for, is my variable in my exponent? You might have, y equals 3 to the x plus 2. That's an exponential. Like if the variable is in the exponent, it's an exponential function. 2 to the x, 100 times 1.10 to the x. So 2 divided by 1 equals 2. 4 divided by 2 equals 2. 8 divided by 4 equals 2. Guess what 16 divided by 8 is? Very good. If the ratio, you can just see, we're multiplying by 2. From here to here, we multiply by 2. 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 That's an exponential function. Non-examples. Again, quadratic, linear. Something like that. This is not a function at all. Doesn't pass the vertical line test, which we will go over later as well. Okay, so now we get to quadratic. Quadratic's a little bit tougher because a quadratic can look distinctly like a exponential function. Just half the parabola would look like an exponential function. it shouldn't be a constant. It should be I'm sorry, this should say linear. And that in and of itself is going to be confusing. We will talk about that in a second. A linear rate of change. Graph is an upward or downward facing parabola, essentially a variable to the second power. It's always squared. The highest power of any variable in the problem is 2. There should be a square right there. Those are all examples. Notice here, so you can have y equals 3x squared plus 5x minus 7. As long as the highest power is 2 of a variable, it's a quadratic. The outputs go down, then up, or vice versa. Should have edited this a little better before I did the video, but here we are. Okay. So we've got some examples, number of games each team of n teams will play in a round robin tournament. Area problems, because like we said, that's the area of a square is any side squared. So that any area problem is going to be a quadratic. There's that. Here's where it's going to get a little funky. There's some bad examples. Okay, what does it mean that the relationship where the quantity is with a linear rate of change? Okay, 0 minus 3, negative 3. Negative 1 minus 0, negative 1. 0 minus negative 1 is 1. Hang on one second, sorry. All right, sorry about that. And then, where my little doohickey go? Sorry. 3 minus 0 is 3. Okay, why does this linear? This is so weird to say that because the rate of change is linear. What they mean by that. So let's go back here. Sorry about this, but it makes a point. Each one of these we added 5. Pretty easy to see. Okay. Oh, and these all should be negative. I'm sorry. These were all negative 5s. Go down by 5. But that rate of change was constant. Here, it's always being multiplied by 2 in this part right here. Well, now the first bit of a rate of change was negative 3, the second was negative 1, third one was 1, and the last one was 3. Well, the rate of change has its own change. Negative 1 minus 3 equals 2. 1 minus negative 1 is 2. 3 minus 1 is 2. So this, the rate of change is linear. That makes it, the original function, quadratic. That is super confusing, and we're going to go over that quite a bit. Always try them. If you can see the same numbers being added every time, linear. If the same numbers being multiplied every time, it's exponential. But then if you try it and you're not sure, but you see the difference here is increasing or decreasing, like the difference between them is increasing. You have to go like a step farther. Find all the differences and then see if those differences change at a similar rate. Very confusing, I know, I apologize. Okay, so now we're going to go back to these. This was the 1 penny today, 2 pennies tomorrow, and we said that was an exponential. And basically what we're doing is it doubles. The previous day is multiplied by 2. So it's going to be 2 to the x, where x is the day. So on day 0, there's 1 penny. anything, this, we can go back over this. Anything to the 0 power is 1. On day 1, that's where we get the 2 pennies. On day 2, we get 4 pennies. On day 3, we get 8, and on and on and on. So that's our exponential. That's why that's exponential. We are multiplying by 2 every time, so it's exponential. The air conditioning unit, so this is an area problem, pi r squared. So because the variable is the radius, and this is going to stay 2, so it's going to be pi times 1 squared, then it's going to be pi times 2 squared, pi times 3 squared. So every minute is increasing. That's going to be quadratic. Our linear is we start with $2.50, and we're adding our miles are being multiplied by 0.35. So that's a good old-fashioned linear. Okay? This one, we just had no pattern to the rate of change at all. Okay, there's that same one. The function, we have now what our linear function is, quadratic function, and we should be all good. There you go.